How's that? Great. Okay, so preparing this talk, I realized that actually the first time I gave this talk was right here, or a version of this talk was right here just before the pandemic. I'm hoping either it's evolved enough to still be interesting to people who are veterans of Western and heard it before, or that it was unmemorable enough that by this stage you've forgotten it and will hear it again afresh. The other thing I noticed, not so much preparing it as looking over it in the last hour or two, is how far Wayne and I, who've been talking about these issues for a long time, have converged. So I think a lot of what I'm going to say is going to be, in some ways, variations on a Mivoldian theme. Hopefully there's enough difference of emphasis and sort of difference of focus that it will, again, still be of some interest to people. Okay, so and I'll move relatively quickly through some of the early stuff that really is very close to things that we've discussed before. So, revising things people have heard already. Dynamical theories are in the business of saying how systems spontaneously evolve and left to themselves. Thermodynamics is not a dynamical theory in that sense. Thermodynamics is what's become a sort of norm to be called in a lot of physics these days a resource theory. In my earlier work on it, I coined the term control theory. Well, not coined, but borrowed the term control theory. I don't think there's a substantive difference there. The point is that a control theory is in the business of describing how what transformations you can bring about in a system by intervening on it externally, by poking and pushing it and manipulating it in a bunch of ways. Wayne and others have already made the case for me that thermodynamics is a control theory in that sense. I'll take that as read. But what kind of control theory? At least the way I'd think about it, it would be analysed. Thank you. It's interested in a particular kind of control problem, which is something like how much energy can I get out of the system? Wayne was talking about productive conversations with philosophers like David Albert when you try to realise that you were talking past each other. And the way David put it was, I was thinking that thermodynamics was about fundamental reality. Now I realise it's about how to get rich, and now it's all fine. So we get rich by extracting energy from the system, or in principle some other conserved quantity, but energy is the usual thing we care about. How much energy can you get out of a system by a given class of control operations? Well, okay, so there's a couple of naive answers. The first naive answer is none. Didn't you look up what the word conserved meant? If energy is conserved, it doesn't change, so how can you get any? Of course, that's nonsense. The whole point about what's going on is that we want the total energy to be conserved so that the system can have less of it so that I can have more of it. And in fact, really, it's only when you have a quantity that's conserved that it really makes sense to talk about moving some of it from one place to another in an unambiguous way, because otherwise you could just be bringing it into existence. So the second answer is, okay, well, if insofar as as it's not a restriction coming from the control operations you have, then there shouldn't be any restrictions at all, because the laws of physics tell us the quantity is conserved. What more beyond sort of boring constraints of just having fat fingers could restrict your ability to get energy out of the system? And of course, the answer we have from 19th century phenomenological thermodynamics is that there are other constraints, that the second law of thermodynamics tells us that it's not just that you can't get more energy out of the system than there is in it, you can't even get as much energy out as there is in it. There's some sort of restriction of how much energy you can get out that is going to require you to leave some energy on the table. And the most succinct summary of the laws of thermodynamics I ever heard was something like the first law says you can't win, the second law says you will always lose except at absolute zero, and the third law says you can't get to absolute zero. But then there are two really different attitudes to the second law that you see across the physics literature and across the philosophy literature. And one very frequent notion is that the second law is an example of an emergent result, an approximate result. It applies at large scales, it applies when we average over large systems, it applies because of limitations of size or limitations of ability. So, it's a combination of large number statistics and the crudeness of the way in which we can intervene. And again, that's tied to the idea that thermodynamics itself is an emergent theory, an approximate theory, that thermodynamics is not a fundamental thing. And so, maybe it can be, for small enough systems, maybe it can be violated randomly. If you're clever enough, it could be violated even systematically in a statistical way. And I think the normal reading of what Maxwell himself had in mind was that, indeed, a sufficiently clever, light-fingered demon could do that kind of stuff. We're just too large, too slow, too stupid. Because we've had various reasons before, I'm just going to say obligatory Maxwell quote. But then there's another sense of the second law, which is it's some kind of exact principle. It's universal. It's a fundamental constraint on physics. And the sort of systematic literature in physics on how Maxwell's demon is, after all, not possible because of constraints coming from information generation or information erasure or what have you, is very much in that kind of flavour. And on that same framework has the second law as something that's applicable to large systems just as much as it is to small systems. And we've seen this in some of this morning's talks. And along these lines, it's impossible to violate the second law, even in principle. Understood, as we'll see statistically. The demons are exorcised, to borrow John Ehrman and John Norton's term. I doubt it's original to them. Obligatory Einstein quote. Obligatory Eddington quote. I thought about just taking the quotes out, and I thought that somebody may never have seen these before. But, all right, so one of the things I want to do in this talk is to sort of try to tease out those sort of aspects of the second law and those aspects of thermodynamic irreversibility and pull aside what aspects of thermodynamics we do want to blame on the fact that systems are big and we are clunky and we have limitations from those things that really do apply as some kind of fundamental constraint. And to try to see in particular to what extent the notion of irreversibility is coming out from one or other of those notions of thermodynamics. And as a kind of spoiler to where I'm going, then I'm going to argue that the irreversibility of thermodynamics is absolutely a consequence of macroscopic goings-on, but that even if we have a fully reversible thermodynamics, there are still hard limits on our energy extraction opportunities that don't simply rely on our limited ability to manipulate systems. I should say that in the spirit of what Wayne said at the beginning of his talk, this is the kind of philosophy of physics talk where I'm not really going to be doing anything fundamentally new. I'm going to be organising and arranging ideas that in various corners are quite well known. I once said to some physicists that the job description for philosopher of physics was to tell them things they already knew and then explain why they were profound things.
They don't know them for the right reason.
That also works. And sort of linked into all of that is I want to just give, in a little bit of detail and sort of adverting to the written up version of this that gives a bit more detail, something a bit quantitative about exactly how the derivation of thermodynamics from statistical mechanics goes. I don't think I'm going to say anything contradictory to Wayne's version of this, but perhaps it's complementary. And I think sometimes you do have the sense in the literature that there's some idea that in principle you could of course derive thermodynamics from statistical mechanics, but it's deeply, deeply mysterious how that happens. Maybe it's deeply, deeply mysterious, but there are some awfully standard calculational moves that are made that are just worth sort of exhibiting and making apparent. Okay, so here goes. I want to start by giving a quick summary of what I take phenomenological thermodynamics to be. I am going to be wildly unhistorical about this. Wayne said if he was in charge, nobody would be allowed to use the word entropy except in the original historical Clausius sense. Wayne is not in charge. I'm going to be using it differently. So here's how I want to characterize phenomenological thermodynamics from the point of view of saying we're not going to give an explicit microphysics just yet, but we're going to get to within a hop, a skip, and a jump of it and describe not thermodynamics as it comes out pedagogically, historically, but what the theory actually looks like when we're using it as an adjunct to various bits of statistical mechanics in physics. And there's various ways you could characterize it, and I wouldn't say this is unique, but I think it's helpful to have something on the table. So in thermodynamics, we have a system that's at equilibrium. We've got this notion of equilibrium that we're just taking as read, and the system is characterized by the value of its energy. It's also characterized by some parameters on the system that are controlled externally. And it might be characterized by some other quantities other than energy that are also conserved. So the canonical example of this is the dilute gas. So the dilute gas at equilibrium is characterized by the energy of the gas. It's also characterized by the volume of the box, and it's also characterized by the number of particles in the gas. And so schematically, I'll use V to talk about the external parameters in general, and N to talk about any other conserved quantities that might be present. There may be more than one of these. In some cases, there may be none of these. There's a certain amount of definitional convenience as to when I want to treat something as a conserved quantity and when I want to treat it as a parameter. So do we want to say, for instance, in the gas, the number of particles is a conserved quantity of the gas, or do I just want to say it's part of how I formulated the problem that there's 6 times 10 to the 23 of them? That's really a setup problem. There's nothing deep hangs on it. And then if systems are not at equilibrium, they spontaneously go to equilibrium. And the equilibrium state is characterized uniquely by its energy, its external parameters, its other conserved quantities. There's something, as a quick aside, it's slightly, when Brown and Nufink state the second law, it's strange that they put it as a system confined to a finite volume will obtain a unique state. There's a lack of generality that comes in the way the philosophy literature sometimes talks about thermodynamics. System size can be an externally controlled parameter, so can magnetic field, so can indefinitely many things. I mean, a few examples just to make the point. So if I've just got a rock, the shape of the rock's fixed, only the energy is a relevant parameter there. The system will achieve an equilibrium state determined only by its energy. A box of gas with a fixed quantity of gas I'm taking as a background, energy and volume. The box with variable quantity of gas, now the number comes in. Box of blackbody radiation, photon number is not conserved, but energy is. So for the box of radiation, there is no conserved particle number, but there's still the volume of the box, and that's still there as a parameter. If I put a ferromagnet in an external magnetic field, I've got energy and field strength. I meant to put up black holes there. A black hole, again, no external parameters, because no one tells black holes what to do. But angular momentum and charge are also conserved quantities, so the equilibrium space for the black hole is characterized by rest frame energy plus angular momentum plus charge. Okay, and then here's how the control theory of phenomenological thermodynamics goes. Control here. Firstly, the obvious piece of the first law, the net energy required to carry out any transition, and remember equilibrium states are entirely characterized by their conserved quantities and the parameters, so we can just think that u, v, n picks out an equilibrium state. Any transition from u, v, n to u prime, v prime, n prime gives us energy equal to the difference between the energies of the system. That's just the conservation of energy. But also, there is a function, a state function, S of u, v, n, the entropy, thermodynamic entropy. The state function is the equation of state. It's defined for each thermodynamic system. It's additive or approximately additive between systems that are isolated or approximately isolated. Any transition between otherwise isolated systems is non-decreasing with respect to this function. So the way I've set this up, I should say, I'm taking the isolated picture of thermodynamics as the starting point. If you want to do thermodynamics in equilibrium for heat bath, knock yourself out, but the heat bath wants to be one of the systems. And then we'll just idealize it to infinity if you want to construct the, in this setup, derivative notion of thermodynamics, which has the heat bath as present. So that's it, really. That I want to claim is pretty much the full content of thermodynamics, phenomenologically given. We antecedently suppose that we understand what the parameters are and what the conserved quantities are, and we understand the entropy entirely through its role as this quantity that determines which transitions are allowable and not allowable. And then we can talk about how one might relate that to other notions. But that's the quite austere version of phenomenological thermodynamics I want to talk about. And I want to claim that for the purposes we use thermodynamics for in contemporary physics, pretty much all of it is caught in this kind of sense. But of course, in contemporary physics, we're not in the business of just postulating that state function. We want to know what it is and how we get it. And crucially, in contemporary physics, we have a recipe for doing it. And I'm calling it a recipe because it's contentious or could be contested where it comes from. it's not contested that it works. And the recipe to review... Hello? It's a strangely haunted experience, this. No problem. My fault for getting to hide things. Yeah. So here's how the recipe works. And by the way, I'm going to largely talk classically, but you can move fairly smoothly between classical and quantum tellings of this story, and the written up version of this paper is systematically ambiguous between the two. So thermodynamic systems are represented classically by a phase space and a family of Hamiltonians on that phase space, and what the external parameter does is parameterize the Hamiltonian. So if you think about the box as an example, it's helpful to think that I won't take the phase space of the box as being finite, spatially finite. I'll take it as spatially infinite, but my Hamiltonian will have a confining potential that rises steeply and without limit at the edge of the box. And then I define this thing called the canonical distribution, which is just given by this familiar mathematical form. People sometimes say grand canonical distribution when you bring in other conserved quantities. I'm not going to bother. Obviously, if there aren't any other conserved quantities, it just reduces to the normal form. And then we define these parameters t and mu so that the expected value of the quantity implicitly defines their value. So you can imagine that the canonical distribution is defined in terms of these real numbers u, v, n, which bear a suspicious similarity to the symbols I use to represent energy and volume and other conserved quantities. But for the moment, just think of them as pure numbers. We set it up so that the canonical distribution is such that the expectation value of the Hamiltonian at this given volume on the canonical state is u, and the expectation value of the other conserved quantities on this state is this value n. So that gives us a function that's defined explicitly in terms of v and mu and t, but implicitly in terms of v and the expectation values of h of v and n. And then the state function is just the Gibbs entropy of the canonical distribution at those numbers. That's the recipe. If you shut up and calculate, they say, if you just write down the Hamiltonian for an interesting system, and you turn the handle of this process, and you actually work out how to do what is usually an extremely difficult calculation, and if nobody's done it before, then and if you then publish it in somewhere reputable, you sit back and sometime later somebody gives you the Onslaught Prize or the Nobel Prize or some other goodies. That's how the game is played. So, why does it work? I'm going to go very briefly over sort of in-principle woes that philosophers have brought to the table about probability distributions, because both Wayne and to some extent Katie have already covered this ground. So we have obligatory David Albert quote. Mine is charitably modified to reflect the fact that milk isn't actually soluble in water.
This is the third time today we've seen this.
Exactly. To review rather briefly things that have come up before, Albert's concern, various philosophers' concern, is that the probability distribution, that something epistemic like this doesn't have any business being part of our foundational theories of the world. But firstly, just because you're using, and this is more relevant for StatMech than thermodynamics, just because you're using probabilities doesn't mean you have to understand them epistemically. Katie was advancing the theory that these probabilities should be thought about as the classical limits of quantum probabilities. I like that story. There are other stories. But in any case, the move that this is an epistemic object is separate from the formal use of probabilities. Secondly, you've got no choice anyway. There's quantum mechanics. It's not as if there's no Parche Bohmian approaches. There is no hidden variable theory that stands to, I suppose, really Parche suggestions in the psiontic framework. There is no hidden variable theory that stands to quantum mechanics as Hamiltonian mechanics stands to Liouvillean mechanics. So you better, even if you don't like objects of this kind, suck it up because we need them in quantum mechanics. And in any case, and Wayne talked about this in a bit more detail, insofar as criticisms of this form have bite in our study of spontaneous equilibration, they don't have bite in a control theory. if you say, can anyone seriously think that our merely being ignorant of the exact micro-conditions of thermodynamics plays some part in restricting the things I can do to the systems in thermodynamics, then as Wayne pointed out, that's a much less compelling argument. So, going on to how one might justify the recipe. So, observation. Hamiltonian control operations preserve Gibbs entropy. Propose, firstly, and again, following physics orthodoxy, firstly, our control operations are indeed Hamiltonian. In other words, what we're doing when we control the system is turn on some Hamiltonian or turn on some perturbation parameter in the Hamiltonian. Some of the control operations we might do might be varying that very parameter V in the Hamiltonian. Others might be varying the Hamiltonian along some other parameter path and bringing it back to some H of V. But in any case, what we'll assume our control operations indeed are Hamiltonian. We'll also assume the system has an equilibration timescale and we're too slow compared to it. So we can't act on the system quickly compared to the timescales on which the system equilibrates. And the naive thought one might have is, well, in that case, look, if equilibrium is described by the canonical distribution, equilibration had better be the evolution towards the canonical distribution. And so, we can come back to that in a second. If that were true, if spontaneous dynamical evolution was the movement of the system towards the appropriate canonical distribution, then you'd have the machinery to understand what was going on here, because not all of our control processes would conserve Gibbs entropy. Spontaneous equilibration would increase Gibbs entropy, and so, of course, nothing you could do could decrease Gibbs entropy. Okay, the reason that's naive, of course, is that insofar as we think equilibration is also a Hamiltonian process, then it also conserves Gibbs entropy. So it can't literally be true that equilibration is the evolution of a system initially described by the canonical distribution to another state also described by the canonical distribution, but at a higher value of the Gibbs entropy. That's not dynamically possible if equilibration is itself a Hamiltonian flow process, and mutatis mutandis in quantum mechanics. But as we've seen suggested, it might be enough to say that equilibration is the evolution of the distribution to something that is indistinguishable from the canonical distribution from the point of view of the, in equilibrium stat mech, from the point of view of all of the macroscopically salient features of the system, from the point of view of thermodynamic control theory, it might be indistinguishable from the point of view of any interventions we can do. In other words, the interventions we do on the system don't change anything in a way that wouldn't have changed if we did them on a system that was at equilibrium. That's a plausible idea. Well, we need to do some work to cash out why it is. If that's true, then again we have an argument as to why you'd expect the standard recipe to work. The system didn't really evolve to the canonical distribution, but it evolved to a distribution that's just the same as the canonical distribution from the point of view of anything we can do to it. Since if it really did evolve towards the canonical distribution, it would follow that the Gibbs entropy couldn't go down, then what's actually going to happen is the Gibbs entropy, again, for any transformations we can do, can't go down, provided by Gibbs entropy we don't mean the actual microphysical Gibbs entropy, but we mean the Gibbs entropy of the canonical state at the same parameters as the actual state. So that's I take it, the sort of relatively standard story about what the derivation of thermodynamic, of equilibrium phenomenological thermodynamic looks like from a Hamiltonian or in quantum mechanics unitary dynamical starting point. And I want to sort of cash that out and generalize a little bit. So I want to introduce the general idea of a coarse-graining map on a space of distributions. The idea here is quite similar from the way it's used in non-equilibrium statistical mechanics in the Morris-Wanzig framework, though I'm not wanting it to be conceptually identical. So a given map J is a coarse-graining map. Firstly, it's a map of states to states, so usual thing. Input a probability distribution on phase space, output a probability distribution on phase space, or if you like, input a mixed state, output a mixed state. And it's a projection, i.e. it squares to itself. So there's a certain special subspace of projections that are the coarse-grained. There's a subspace of distributions of the coarse-grained distributions, and what J does is dump your state into that space, and if your state's already there, it stays there. J leaves the energy invariant, and in fact, I haven't noted it here, but any other conserved quantities invariant. And J is entropy non-decreasing, Gibbs entropy non-decreasing. So when I coarse grain, the Gibbs entropy never goes down, and it goes up unless I started with a coarse-grained state initially. That's what I mean by a coarse-graining map. For the moment, that's just a purely formal definition. And just, to give the clear example that's relevant here, equilibration is a coarse-graining map. So equilibration takes the actual distribution and replaces it with the canonical distribution at the same expected value of energy and other conserved quantities. And the Gibbs entropy, the canonical distribution maximizes Gibbs entropy for a given set of parameters, so the equilibration coarse-graining satisfies those characteristics, so it's a coarse-graining in my sense. Why do I want to introduce this bit of machinery? Because I want to introduce the idea of a coarse-grained control theory. As I want to use my coarse-graining map to specify a control theory, or at least to specify a constraint on a control theory. And I want to say, look, I've got a collection of control operations. All of these are Hamiltonian evolutions of the system, or unitary evolutions. And that set forward commutes with the coarse-graining if basically it doesn't make a difference whether I act coarse-grain, act coarse-grain, act coarse-grain, act coarse-grain, or if I just act, and coarse-grain right at the end. So the idea here is if my control theory forward commutes with J, then I can't control any features of the system unless they're insensitive under the action of J. So if I can control the system in a way that influences its J coarse-grained features in a way that's different whether I act on the original state or the coarse-grained one. In other words, if I can have two different states that coarse-grain to the same thing, but I have a way of acting on this one so it coarse-grains to this thing, and that one so it coarse-grains to that thing, then my control operations don't forward commute with the coarse-graining, then I have the ability to control some features which are washed out by J. If that's not true, it means the only things I can control are the things that are J invariant. Ideally, you define this so you could have an arbitrary sequence of control operations concatenated to satisfy this rule. If you think a bit about Poincare recurrence, you'll realize that's not possible. But it is possible to say for some fixed, finite, tacit, but ridiculously large number of iterations, I can do this. And I also want to say, the thing I said actually combines both of these kind of operations. The state is going to be forward compatible if the particular state ends up in the same place. So think of this as a joint consideration. I've got some states that are forward compatible and some coarse-grainings that are, and I can iterate and get to the same place. It's possible that you could have some. If you think about time reversal operations and weird anti-thermodynamic states, it's possible that even though my operations forward commute with coarse-graining, I could prepare some very weird state, but nonetheless, if I start with that state, things don't work out the way they're supposed to. Notice I've got J on the left-hand side. Sorry, I've got J on the far right on the top row, and not on the bottom row. So, if the initial state is itself a coarse-grained state, then the second line would follow from the first. We don't want to assume that, but we want to assume, in fact, J doesn't have the initial state doesn't have some secret features that make the whole thing fall apart. So those are the two halves of the story. That's what's going on in saying my control theory forward commutes with the coarse-graining for a given set of states. And notice that if the control operations are forward compatible with J, then they're non-decreasing in the coarse-grained entropy. So the coarse-grained entropy of a state is just the Gibbs entropy of the coarse-graining of that state. And so if I've got a control theory that forward commutes with the coarse-graining, and I start with a state that's forward compatible with the coarse-graining, and I evolve it under a series of control operations, the coarse-grained entropy is non-decreasing. So it's worth just pausing there, because when one runs into these notions of coarse-graining in the foundational literature, one's often worried that one's saying, we'll suspend the Hamiltonian dynamics of the system, and we will instead evolve it by a new dynamics that genuinely involves coarse-graining. That's not what I'm saying here. The coarse-grained entropy is genuinely a function of the fine-grained distribution. You know, it's a function in the straightforward mathematical sense that if I give you a fine-grained distribution, you can give me back its coarse-grained entropy. Mathematically, in thought, you do that by coarse-graining it and then calculating the Gibbs entropy, but it's still mathematically a property of the fine-grained distribution. And the claim is that the ordinary unitary / Hamiltonian evolution of the system under the control operations, with no intermediate coarse-graining actually happening, is non-decreasing and generically increasing in coarse-grained entropy. So the point is not that we're actually doing the coarse-graining operations, it's that as far as the coarse-grained features are concerned, we might as well have been. It wouldn't make any difference. We get to the same place if we did it. So for reasons of time and because doing mathematics on the board doesn't always work, I'm not going to go through the details of that. I hope it's reasonably intuitive, and the details are in the paper. You can kind of see what's going on, can't you? If it does forward commute, then every time I evolve unitarily, the Gibbs entropy doesn't change. Every time I coarse-grain, the Gibbs entropy goes up. So the process of evolve coarse-grain, evolve coarse-grain, evolve coarse-grain definitely increases the Gibbs entropy. And if it forward commutes, that's the same as the process of just evolve coarse-grain. So claim, this gives us a large framework to think about a whole bunch of thermodynamic control theories where we're going to find equilibration control theory, the theory that underpins phenomenological thermodynamics, as just one of those theories. So here are some examples of theories of this kind. So equilibrium thermodynamics is just going to say my coarse-graining maps the state to its canonical state. And you want to think that equilibrium thermodynamics is going to be the theory where my control operations are forward compatible with equilibration, which means I can't get at features more fine-grained than the big bulk features of the system, and I also can't get at the system faster than it equilibrates. So although the system might not actually be at equilibrium, it doesn't help me much because it'll get to equilibrium or get to something that from my point of view is indistinguishable from equilibrium before I have a chance to do anything clever. The system's fast, I'm slow and sluggish. Here's a slightly more fine-grained framework. You might imagine I've got a system consisting of a bunch of subsystems, and I do have enough control of the system to keep the subsystems isolated. So imagine I've got like a box of gas here and a box of gas here. Now, if some idiot has welded them together with a conducting medium between them, then plausibly I actually can't, even if they happen, say, to start at different temperatures, I can't get at the system fast enough to change the fact it's just going to equilibrate at the same temperature. And so in that situation, the right coarse-graining is just global equilibrium for the whole system. But if the boxes have been conveniently separated, or I have the presence of mind to slam an insulating medium into the gap between them quickly enough for it not to matter, and then to move that insulator around as I feel like it, now the right coarse-graining is going to be the separate equilibration of the two systems and not the combined one. In Boltzmann's way of, Boltzmann did many things. In what is sometimes called Boltzmann's way of doing things, in what sometimes gets called the Boltzmannian approach to statistical mechanics, we coarse-grain phase space into cells, and then there's a coarse-graining that basically smooths the distribution out across so that it's uniform in each cell. So that might be the right distribution to use if I can control the system at the level of its individual macrostate, but not more finely than that. So for instance, imagine a situation where, as it happens, the box of gas has all the gas in the top left corner, and I happen to know that, and I have really fast reflexes. Well, then I could slam a partition in fast, confine it to the top left corner, and then reversibly extend the partition and get some work out. So if I have that level of control of the system, then the appropriate coarse-graining to describe my control theory is something like the Boltzmannian coarse-graining, which is a finer grain notion than the equilibration notions. And the other extreme is reversible thermodynamics, where I can do absolutely anything to the system, and where the, quote, coarse-graining operation is just the identity operation. So that would be the appropriate thermodynamics, sometimes applicable to discussions of Maxwell's demon and things, where I have kind of godlike powers. I can't violate the laws of physics, but I can bring in any Hamiltonian I feel like. Okay, we could say something rather general about how much energy I can get out by these various control operations. So As I mentioned earlier, the canonical distribution maximizes Gibbs entropy for given parameters and conserved quantities. I mean, under weak assumptions, there are minor assumptions you need to make about the state space of the system. Under reasonable assumptions, it maximizes Gibbs entropy. Actually, sorry, I'm the other way around. Unconditionally, it maximizes Gibbs entropy. If it maximizes Gibbs entropy for given energy, it looks unsurprising that it might minimize energy for given Gibbs entropy, and that's true under reasonable assumptions. There are exceptional counter cases. Negative temperature laser systems are awkward. So that being the case, the best way I can get energy out for a given coarse-graining using a control theory compatible with that is to transform the system as carefully as I can to a canonical distribution with the same J entropy as the one I've got. I can't do better than that because I can't decrease J entropy because my control theory is J compatible. So the best I can do is try to get the system to that state with the least energy for given J entropy. Because I get out all the energy that's the difference between the current state and the state I transform into. So I can't reduce J entropy, find the lowest energy state with the same J entropy, and head for that state. Maybe I can't do that, because maybe my control theory is more restrictive even than that coarse-graining, but that's the best I can do. And let's define the free energy of the system with respect to J. This is very close to the available energy notion that Wayne was talking about. The free energy of the system with respect to J is the difference between its actual expectation of energy and its the expected energy of the appropriate canonical distribution. That row there should have a UVN index. So the free energy is equal to the actual energy minus the energy of a canonical distribution at the same J entropy. So notice the amount of free energy that's available is dependent on the appropriate coarse-graining, which is, as we might hope in a control theory, the amount of energy I might be able to get out of the system depends on the kind of control operations I can do. And I'm characterizing my control theory through its coarse-graining operation. So the best I can do is, as reversible as I can, transform the system to this canonical state, pocket all the rest of the energy, and then I'm done. After that, the only way I could get energy out would be to adjust the parameters of the system. As long as I'm trying to get energy out without adjusting the parameters, the best I can do is get the free energy out. And generally, we don't do that well. In fact, as Wayne was pointing out, we probably never do exactly that well. In some control theories, it might be we can get arbitrarily close to doing that well. We'll never do better than that. Work extracted by a J-compatible theory, less than equal to the change in free energy with respect to J. Just pause briefly to note, incidentally, Wayne was talking about the importance of the canonical distribution and that people should think more about it in philosophy. I totally agree with that. One really important thing to notice about the canonical distribution is it's doing two things. It's firstly, it appears to be that distribution which correctly describes at least the macro properties of systems which spontaneously, left entirely to themselves, approach equilibrium. And it also describes that state such that that actively, non-spontaneously, transforming to that state, or as close as you can get to that state, is the best way to get the energy out. So it's characterizable in control theory as the minimum free energy state, and it's characterizable in non-equilibrium statistical mechanics as the state to which things in fact spontaneously go. So while there really is a fundamental difference between thinking of thermodynamics, a control theory, and equilibrium statistical mechanics, a dynamical theory, there are deep and subtle connections between them. So now revisiting equilibrium thermodynamics from that point of view. In equilibrium thermodynamics, there's no free energy at all. The free energy is the difference between the energy of the actual state and the energy of the canonical state at the same Gibbs entropy. But in equilibrium thermodynamics, the coarse-graining is just throw the system to the canonical state with the same Gibbs entropy. So there's no free energy in equilibrium thermodynamics in this sense of it. The only way I can get energy out is by changing parameters or other conserved quantities. So this is the classic, if I got a box of gas, I could certainly get energy out of the gas. In principle, I can get all the energy out of the gas if I just expand it out and out and out and out reversibly. But I can't get energy out without adjusting the parameters. And of course, the the space physically or literally or figuratively to adjust the parameters is itself a scarce resource. I mean, if my proposal to solve the Earth's energy problems is to take a box of gas and expand it until it's the size of the solar system, then there may be some practical problems. In partial equilibrium thermodynamics, which remember is where our coarse-graining lets a whole bunch of subsystems approach equilibrium separately, but doesn't require them to approach it globally, now there's a bunch of free energy available, provided I've got subsystems that have different canonical temperatures and or different chemical potentials. If that's true, I can put two systems together, I can reversibly allow energy or other conserved quantities to flow between them, and I can pocket the difference. But again, what I can do, notice, if I've got a system that consists of a bunch of systems individually at equilibrium, or potentially even individually not at equilibrium, but all I've got is local equilibrium control theory, on a one-off basis, I can take that system, reversibly transform all the systems so they're in equilibrium with each other, eat the free energy, or sell it on the eBay or something. I can only do that once. Once I've done that, the system is now at global equilibrium, and there's no more free energy available. And at that point, the fact that I've got this oh-so-clever control theory is no use to me. At that point, I can't do anything more that I couldn't just have done with the original global equilibration control theory. And again, notice if we let that stuff happen irreversibly, we'll leave free energy on the table. If I've got all these boxes set up this way, and my idiot grad student comes in and just puts a couple of the boxes in thermal contact and then goes out for coffee, then that thermal energy, that free energy is irreversibly lost as long as the only control operation I have is characterized by being forward compatible with J. If you do Boltzmannian thermodynamics, now if the probability distribution over the macrostates doesn't match the canonical distribution, now I've got free energy again. So again, go back to revisit the example from a moment ago, if in fact all the particles are in one corner of the box, and crucially if I know that fact, and if I have Boltzmannian coarse-graining compatible control theory, that's the point when I slam a partition down, reversibly allow the system to expand to fill the box, extract the energy as a consequence. Again, I can only do it once. Once I've done it, then I'm back in the global equilibrium coarse-graining situation. But one off, I've got some free energy. So, the finer my coarse-graining, the more free energy I can sometimes get out if the system happens to start in a friendly state and if I know that fact. And again, to get it out, I need to move reversibly. If actually I just can't be bothered and I let the gas expand, the free energy is gone, I'll never get it back. In the limit of reversible thermodynamics, if the actual fine-grained probability distribution doesn't match the canonical distribution, I can always get free energy out. In reversible thermodynamics, I can apply any transformation I like. So if, in fact, I know the distribution, and it's not the canonical distribution, I can always steer it reversibly. Well, you should be careful here. There are more, as we see in the single shot context, there can be more conserved quantities than just the Gibbs entropy. I should say the best I can do would be if I were able to reversibly steer it to the exact canonical distribution. Maybe I won't even be able to do that, but that's the most I can do. And for large systems, it tends to be you can get arbitrarily close to that. So in any case, I've got more or less any difference between the probability distribution and the canonical distribution is usable for me to extract the free energy. But again, only once. Once I've done, I'm back to a canonical distribution. I'm back to having no available free energy. I'm back to the only way I can get energy out to let the box expand. Unlike the other cases, you do get second chances. If you accidentally let the system evolve in a way that left some free energy on the table, you can always go back for it later. Because all the processes are reversible here, then although the theorem is still totally general, all of our processes are entropy none decreasing. They're also entropy none increasing. So if I've transformed the system to a distribution that's not the canonical distribution and therefore not got out all of the free energy, I can always go back and get it out. So there's a rather general theme I want to bring up here, which sort of goes back to both to Wayne's talk and to Marcus's talk this morning in a different sense, which is the sense in which information about the system is a resource. In America too long, is a resource. So if our control theory is forward compatible with J, what matters for getting work out of the system is the coarse-grained entropy J and the energy. So information about the system is a resource I can use, but only insofar as it's information about things I can manipulate, which is to say information about how the actual state differs from its coarse-graining is useless to me. If you tell, if Shelley Goldstein's angel tells me the exact microstate of the box of gas, but all I have access to is equilibration coarse-graining, that's useless to me. If the angel tells me the exact microstate of the gas and all I have access to is Boltzmannian coarse-graining, it's probably very close to useless to me. If actually I luck out and the angel tells me and it just so happens all the gas is on this side of the room, woohoo, I've got some free energy I can get out. That information was useful to me, but usually it won't be. If I have reversible thermodynamics available to me and the angel tells me the exact microstate of the gas, now I'm laughing. Now I can reversibly transform the gas pretty close to absolute zero and snaffle pretty much all the energy. So you've got this duality where the information is useful to me insofar as it gives me more flexibility. And just to summarize that for these systems, insofar as we want to say, did the entropy go down when you were told the information by the angel? Well, what's your coarse-graining? What's it forward compatible with? If your coarse-graining is forward compatible with J, and if you can kind of get close to the limits of something that's forward compatible with J, then the relevant entropy is the J entropy. So if the J entropy of the state the angel gave you is lower than the J entropy of the equilibrium state, now you can get resources out. So the right answer to the question of whether the entropy went down is going to be, did the entropy relevant to your control operation go down? If it did, that's a genuine resource. So this is a sense in which, while I think the flavour of what I'm doing is close to Wayne, the detailed implementation is quite different because I've got entropy here much more front and centre. I'll just give us a quick sort of realistic example of this. Most of the examples often involve these crazy Maxwell demons. Here's a realistic example. I've got a box of chlorine gas and another box of chlorine gas. Chlorine is a stable mixture of two isotopes. If you tell me that actually this box is entirely chlorine-35 and this box is entirely chlorine-37, if you calculate the fine-grained entropy of that, the entropies are lower. Should I say that the thermodynamic entropy has gone down? Well, it depends on my control theory. If I have access to membranes that permit the passage of chlorine-35 but not chlorine-37 and vice versa, well, now I can actually get energy out of the system because I can reversibly allow the chlorine-35 to expand into the right half of the combined box, and I can reversibly allow the chlorine-37 to expand into the left half of the box. And so it makes sense to say the entropy is lower, and it makes sense to use as my entropy that measure of entropy whereby it has actually gone down, which with this case would be the J entropy for equilibration, where I'm allowing a partial equilibration where the separate amounts of the two gases are conserved. If I don't have access to those membranes, it's useless for me to know that fact, and I can't get anything out. And so the correct entropy I should be using is the one defined by the coarse-graining that doesn't preserve number of chlorine-35 and number of chlorine-37 separately, but only the combination of the two. And conversely, if I do have those membranes, but you just give me the box of gas and they're already mixed, then having those membranes is useless to me. Because although in fact I could have used them to get something out from an unmixed box, as it happens this box is mixed already. There's no free energy available to me, even though I have this control resource. Okay, so I'm mostly done. Let me illustrate these notions by going back to the Maxwell demon notion, because I've argued here that depending on the thermodynamics I have, and depending on what the state of the system is, or at least as I know it to be, then there might be some free energy I can get out, but I can only do it once. So now go back to sort of classic statements of the second law of thermodynamics. I mean, if you think about the second law of thermodynamics as being something like, is there a process by which I can extract energy from a heat bath cyclically, which is to say that I can just keep running and keep getting more and more and more energy out? The answer is going to be no, even if I have access to completely reversible thermodynamics, even if I have total control. Because the fact it's a heat bath is to say, by definition, its state is canonical or not known to me not to be canonical. So it might be that I know an awful lot about my own system. It might be, for instance, that I know my system has an enormous memory bank that that's all initialized in the zero state, such that I can record information about the state of the heat bath in that memory state and use that information to reversibly transform the heat bath to a lower energy state. But all that I'm really doing there is extracting the free energy from my device. And I can only do that once. It might be that my device has some free energy in it. It might be that my device has some free energy in it in the sense that it contains an incredibly sophisticated Maxwell daemon plus memory. It might be my system has some free energy in it in the sense it's just a bit colder than the heat bath. And there's no real fundamental difference between those two from the point of view of reversible thermodynamics. And so a constraint like the sort of classic Clausius or Kelvin statements of the second law, expressed in the kind of way I'm stating them, is just doesn't. It's a consequence of the basic reversible dynamics. It doesn't care about the coarse-graining. So I said I wanted to say something about reversibility and irreversibility. The irreversibility in thermodynamics, in the way I'm describing it, is coming from the coarse-grainings, from our finite manipulative capability, from the fact that we, finite beings, leave free energy on the table and thus end up doing things irreversibly. But the Clausius and Kelvin statements of the second law don't rely on that irreversibility. They're not inherently irreversible statements at all. The irreversible claim is the claim that they're not always saturated. They're hard constraints, even if you don't have access, even if you have access to very fine-grained micro resources. So to sort of illustrate, and actually this is an example I think I originally used in the first version of this talk I gave in London 5 years ago, this London. Can we build a Maxwell daemon? Well, there's two sorts of Maxwell daemon that show up in the philosophy literature, and they tend to get mixed together. A daemon of the first kind can decrease a certain coarse-grained entropy. So fix a J. A daemon of the first kind with respect to that J can decrease J entropy. This is the main useful thing you can do with a daemon of the first kind. If you ever run into a physicist who says, no process can ever decrease entropy, you can say, aha, look at this one. I have a daemon of the first kind. It can reduce entropy. Daemons of the first kind are not barred by any particular physical principle. All it means if I have a daemon of the first kind is that when I said my control theory was forward compatible with J, I was lying. A physical system is a daemon with respect to a coarse-graining J if the daemon has access to finer-grained control operations than J characterizes. So in that sense, for instance, if J was just global equilibration, then the person with the semi-permeable membranes that let chlorine 35 through and not chlorine 37 is a Maxwell daemon. They have access to a control operation such that they can decrease entropy with respect to something coarser-grained than that. So daemons of the first kind are fine. A daemon of the second kind can violate the Carnot inequality and heat transfer, or it can violate the Clausius form of the second law, and it can extract energy indefinitely from a heat bath, or it can cause energy to flow from a colder system to a hot system indefinitely. Here's the main use of a daemon of the second kind. A daemon of the second kind allows you to charge your phone from the ambient air. It allows you to run a power station that literally cools down the environment and emits it down the wire. It allows you to be quite economically successful. It probably causes the government to come knocking on your door quite quickly. Daemons of the second kind, for better or for worse, are impossible. Okay, let me sum up. The irreversibility in thermodynamics isn't just coming from equilibration, or not directly, it's also coming from the time asymmetric constraints on our control operations. I'm not particularly suggesting anyone is saying it just comes from equilibration, although some of you occasionally see statements adjacent to that in some of the philosophy of thermodynamics literature. But in any case, it's not just that the process of spontaneously going from non-equilibrium to equilibrium is a irreversible process, it's also the case that many of our control processes can't be performed in reverse. Indeed, that's in many ways the essence of what we have in mind when we talk about the irreversibility of thermodynamics. And of course, those constraints would have to be grounded in something like a stat-mech asymmetry, and that's not something I've talked about. But that irreversibility, which is genuine irreversibility, and genuinely comes from the thickness of our fingers and other constraints of our ability to manipulate systems, that ought to be sharply distinguished from the hard constraints that come out of those versions of the second law that don't just say a certain form of entropy can't increase, but directly say you can't get something for nothing, you can't get out usable energy in some indefinite sense from the heat bath. Those versions don't have anything to do with irreversibility. In fact, those versions are really true only because our underlying dynamics is reversible. And this is something that's recognized in the physics literature, but is, I think, always worth stressing. If I genuinely had access to an irreversible microdynamics, I could take a system whose probability distribution is smeared over a very large number of states and map all of those states concurrently to the same zero energy state. At the most basic kind of intuitive level, the reason there are constraints beyond conservation of energy on my ability to get energy out of a system is because the system could be in a bunch of different states. And if I've got a control operation that maps this state to the lowest energy state, the best I can do with this state is put it in the second lowest energy state. And the best I can do with this state is put it in the lowest energy state. I can take my probability mass up here as a rather high energy, and I can move it down to here. But because it's reversible, because I can't make it any smaller, it's going to stick out some. And that's leaving energy unavailable. That's happening because of microphysical reversibility, and it's microphysical reversibility which is at the root of the universe's inconvenient constraints about our ability to get something for nothing. Thank you, I'll stop there.
Thank you very much for the talk. Just a clarificatory question of when you talked about Boltzmannian thermodynamics versus, say, reversible thermodynamics and all these different coarse-graining, are these different interpretations or different theories entirely? I didn't follow that bit, I'm afraid. Thank you.
They're absolutely different theories. They're different control theories that are available to agents who have different capabilities. So whether you have access to equilibrium control theory or Boltzmannian control theory or fully reversible control theory is a totally objective hard fact about the things you're capable of doing. If you do have access to reversible control theory, there's some labs who'd like to talk to you.
Okay.
Why don't I take it up to whoever asked the question? That's probably simplest, isn't it?
Good. Questions? Okay, now, not just grad students, anybody.
Oh, yep.
So with all the very wonderful talk about what agents with certain capabilities can do, controlling certain thermodynamic systems, how far along are we on knowing what agents could be, given the same laws of physics, given that the agents don't actually sort of step outside the natural world? Like, how well can we say such and such kinds of agents are actually feasible?
Good. So the short answer is going to be not terribly far. The slightly more substantial answer, I think, is going to be I don't think physics, or at any rate, I don't think thermodynamics is going to give us constraints of that kind that go much beyond the constraints of which Hamiltonians could carry out. Because in a certain sense, the question becomes, okay, if real agents have access to less than all possible Hamiltonians, what are they going to not have access to? And that's going to be a question that is going to be extremely cross-disciplinary. There will include biological constraints come into play for some systems. Issues of the tensile strength of certain nanoscale substances probably come into it. So I wouldn't expect something very general to be sayable at this kind of level. But we've been wrong before. Sometimes one's pleased to guess at something. But I don't think it would be absurd to try to look for some sort of level of generality claims that nonetheless constrained the kind of operations that can be done. I'd be surprised to find it in this kind of corner of statistical mechanics at any rate.
I'm just wondering, does the first point imply that a past hypothesis will not even be enough to explain the full irreversibility of quantum mechanics? So you need more than a past hypothesis if you want to put to claim that thermodynamics has something to do with error of time, and would you need more than the past hypothesis, because the past hypothesis will explain why things tends towards equilibrium, but not necessarily the constraint on control operations?
So I think to ask the past hypothesis just to explain that systems tend to equilibrium is to ask much less than it's traditionally taken to give. I mean, non-equilibrium statistical mechanics is systematically reversible. The dynamical processes it describes don't work backwards in time. The cleanest examples of those are a flat-out equilibration, but there's a lot more than that. I mean, all the Navier-Stokes equation is an example, for instance. So an adequate grounding of non-equilibrium stat mech is going to have to give us all of those various dynamical irreversibilities at the mesoscale. I would expect that in doing so, it ought to give us adequate understanding not only why the systems we're dealing with in Wayne's terms, Maxwellian thermodynamics, spontaneously go to equilibrium, but also why the various ways we can control systems display a directedness to them. Now, the directedness, if you like, the fact that our control is crude, I don't think needs to be tracked to something like a past hypothesis. That can just be that we have fat fingers. But the fact that our control operations are themselves directed, that the very fact of phrasing something as a control theory, as I think Wayne said in the previous discussion, presupposes a certain directness of time. That's something I would anticipate being resolvable as a downstream product of having a systematic resolution of the direction of time in non-equilibrium statistical mechanics, although that's conjectural without it. But in any case, I don't think, if, for instance, the past hypothesis is an ultimately satisfactory grounding for the asymmetries in statistical mechanics writ large, and I think at least some form of the past hypothesis probably is, then that ought to get us out spontaneous equilibration, but also the fact that agents exist and have a directedness of their interventions.
Thank you. I really found the talk quite clear and interesting, but maybe less clear now that I've seen this last slide, because there's one question I do have. So the relationship between points 1 and 2 here. So why do the time asymmetric constraints on control operations need to be grounded in a statistical mechanical asymmetry? I feel like maybe that's something.
Oh, I see. Yeah, okay, so that second conclusion is not something I've independently argued for. It's completely compatible with my description that the asymmetry of intervention is grounded in the fact that we're children of God and are beings who have been granted grace to act through time in only one direction. I'm assuming for separate reasons I haven't argued for that macrophysics in general, including the macrophysics of agents, is the kind of thing that needs to ground out in microphysics. And then since the macrophysics of agents is just demonstrably manifestly irreversible, we'd expect that fact to be just one of the large family of irreversible features of physical systems that we'd look to ultimately to non-equilibrium stat mech to give us a grounding for. But no, you're right, that isn't really a conclusion of the talk, except in the sense that it immediately follows from the first via a whole bunch of other premises I hadn't stated and was largely taken as read.
We have a question here.
I didn't really understand early on in your talk, I didn't really understand why the definition of forward compatibility with a J was only assumed or only predicated of certain sufficiently large strings of interventions.
Good. Okay, good. So if I've got, I don't know if I can give you a rigorous theorem to this effect, but if I've got some finite, probably can actually. If I've got some finite system, and let it be quantum here because there are classical loopholes, but I don't think they matter very much. If I've got some system with a finite Hilbert space, and my control operation is some operation u, then there'll be some n such that u to the n is extremely close to the identity. And at that point, if I start with a coarse-grained state, I act on it with u that many times, I'll get back to pretty much the same coarse-grained state. Whereas if I act on it with u, coarse-grain, act on it with u, coarse-grain again, I'll get back to a very different state. So it's basically, Poincare recurrence rules out the idea that you could have a genuinely infinite sequence of this kind. But again, because the relevant timescale is the recurrence timescale, we can expect it to be kind of satisfactorily long for realistic size systems. It's an annoying technical lacuna. It would be much more elegant to formulate the framework as saying I just have a set closed under composition. But
right. So the way the definition worked was there was like existentially quantified over capital N, and everything.
Could you speak up?
oh, you need the microphone back, won't you? Yeah. There you go.
So strictly speaking, the way the definition worked was there's some N given to us, existentially quantified, and then but then it's universally quantified over strings of intervention, or strings of Hamiltonian operations, n-fold, and anything sufficiently large than larger than n will work. And like n's like a minimum threshold for the lists of U's.
Yeah, I'll put the definition back up.
To be forward compatible.
You need to give me control again. Here we go.
So n is some sort of minimum, and then you're universally quantifying over all collections of U's whose size is larger than that n?
Is less than that n.
Is less?
Smaller than that n.
Okay.
So my
Okay, that makes way more sense actually. Okay.
Yeah. So I've got some fixed collection of operations. I would love that collection to be closed under composition. That can't be true. I've got a fixed collection, and I want to say for elements of that collection and sequences of elements of that collection of length less than finite fixed n, then these properties hold. And n is like subrecurrent, so n could get away with being 10 to the power of 10 to the power of 30 or something.
Okay, right. So I thought that was a minimum.
No, it's exactly the opposite.
Right.
The small number of control operations, where small is a very permissive restriction, satisfy this condition. Sufficiently large ones can't on pain of Poincare recurrence.
Right. Okay.
More questions? Comments? Okay. Well, thank you very much. This is really, really